talking about what I've been working on to start answering this question, a little bit of the methods that I'm using, and the progress that I've been making. And so really what I've been doing is looking at, so I'm going to talk a little bit about what I mean by model fit, along with the questions that I'm thinking about applying it to. And for most of the talk today, I'm going to be talking about the molecular side of things. But I also, some colleagues mentioned that looking at the morphology and model fit of the morphology would also be, this would be a really valuable system to start looking at that. So what do I mean by model fit? For phylogenetics, we have kind of some basics parts. You start with the data, the model, and the tree. And so by model fit, I mean how well do these models of evolution fit the data that we're using? And it's a question that kind of came up when phylogenetic models first started, we first started coming up with different kinds of models, but it hasn't really been addressed since then, except recently by my advisor, Genevieve, has kind of started to bring it back into the forefront. And I think it's really important to think about in this age of big data. So here's an example of early metazoan evolution, and you can see that there's a couple different large data sets, or decent-sized data sets, that give us different trees with high support. And this isn't the only example of that. And so it kind of speaks to the point that we can't just use these support values that we've been using for our trees anymore to say, oh, we're really confident in this tree, it's the right answer, it has high support values. We're getting different trees with high support values, and I think that's where model fit can come in and kind of help start to identify confidence in different loci or different types of data, or in different models if there's a model that is just fitting really poorly across all your data. And so I'm going to go a little bit about what I've been using for model fit. So the difficulty with model fit in phylogenetics is we don't really know what our expected distribution of sequence alignments is supposed to be, right? Like, is it a normal distribution? Should we be using chi-squared? And part of that is trying to figure out what parameters to use. So instead, we've been using a posterior predictive approach, which is basically taking your empirical data and your model and creating an expected distribution. And so then what you do is you compare your expected distribution to your empirical data and kind of get a sense of how well your model is predicting the processes that are creating your data. And so there's a couple of different ways to compare your distribution to your empirical data. And that's with summary statistics. And there's two different flavors, really. There's database and there's inference-based. And so with database, you're looking at characters of the data that you're interested in investigating, like site frequency spectra or something like that with multiple sequence alignment. And then the other type is inference-based. And for phylogenetics, that generally is trees. So you're looking at aspects of the tree, like tree-to-tree distance within the posterior, or other things like that, and then comparing all the trees that you've inferred from your expected distribution to your empirical value. And I think I forgot to mention the expected distribution also called the posterior predictive distribution. And so it's a little bit intuitive in terms of if your empirical value falls within your expected distribution, then you have pretty good confidence that your model explains your data well, and it's a good fit. And there's not any sort of violation of assumptions that are biasing your data, or biasing your inferences. And then how far away your empirical statistic falls in your distribution can kind of give you a sense of how poor the fit the model is. And then you can compare across loci. And so it's currently been a couple papers published from our lab on this, but the current workflow is not exactly simple. The slide is a little overwhelming, and that's basically how it is trying to do these analyses at the moment. And so it's a fairly simple process from data to your expected distributions, but the current workflow has multiple different programs and multiple different in-between scripts because you're generating a lot of data files with your simulated expected distribution. And keeping track of them is a little bit difficult. I had a crash course in Bash programming, getting all of this worked out. And so part of what I've been working on for the last couple months is helping to get all of this incorporated into RevBase, which I think is going to be a really valuable tool So I've become a little bit of an entomologist on the user end of things, finding bugs. But I've also had a lot of fun because once this is pretty much fully incorporated in RedBase. I think we found the last bug, so I'm quitting my entomology job soon. But once this gets implemented in RedBase, all you have to do is input your multiple sequence alignments along with a model. And the really exciting thing is you can input any type of model that you want. You're not limited at all. And the other exciting part is that RedBase will output both your expected distribution of sequence alignments along with an expected distribution of trees. And currently then the comparison step that I mentioned before is done in a separate program, but there's some other people in Dr. Brown's lab who are working with the developers of RedBase to get that step also incorporated into RedBase. So it'll be one simple pipeline, and I'm really hoping that it'll be a step that's incorporated more often in phylogenetic analyses, especially with these large data sets when there's lots of variation. And so what I'm interested in applying it to is the Squamate tree of life. And so a couple years ago, there were two different papers that came out, one on the morphological data set, and then one with a molecular data set. And they really varied in terms of most significantly, the placement of iguania. And the placement of iguania really tells us completely different things about how lizards have evolved, right? There's two very different hypotheses in terms of the evolution of venom, ecology, behavior, morphology, a lot of different things. And so what I first started to do was look into the further research that's been done with the molecular tree, and there's been a couple papers since then looking closer into the molecular data, and there's really not any gene support for the morphological placement of iguania. For the most part, even adding more loci and more taxa, you still tend to get the same tree with iguania up here by serpents and angleworms. And so now what? And I think this is an interesting place to start looking into model fit. And so that's what I've been working on is, I have managed to get gene trees out of RedBase, just the empirical trees, and they all do support this placement of iguania just to replicate what's already been published. And then the next step will be to create posterior predictive distributions and do a model check across all genes. And I'm also interested in looking at a summary statistic that's being developed in the lab, looking specifically at branch support across trees, and using that as a summary statistic, especially in the case of iguania, just to see if there is consistent support across gene trees and if that correlates with model fit. And so the other thing that I've been talking about and thinking about recently is applying all of this also to the morphological data, because the process of this posterior predictive model check can basically be done with any model that can be implemented in a Bayesian framework. And so this Squamate tree provides a really valuable resource, an example to check, to compare the two different data sets and look at model fit between the two and get some sort of general feeling of which one that we should have more confidence in. And so, like I mentioned, I'm still working on getting the results for this, but the potential outcomes is if we're going to believe what the molecular tree has to say and believe that this phylogenetic hypothesis is accurate, then you're going to expect that for the molecular data, you're going to have pretty good model fit across all of the different genes, and any poor model fit won't necessarily be correlated with any specific topology. And you would expect that if the molecular tree is correct for the morphological data, you would see poor model fit for the most part across all the morphological data, indicating that there's some sort of systematic error going on causing this topology. And then if the morphological tree is correct, you'd expect kind of the opposite, where the molecular data will show poor fit across most loci, and the morphological data will have a good fit across most of the characters. And then, of course, if they both have poor model fit, there could be an alternative hypothesis or tree that pops up as showing good model fit. And so just a quick summary. I've been working to get these posterior predictive model checks implemented in RedBase and getting that pipeline down, which I think will be really valuable and hopefully user-friendly is another thing. And it'll provide an objective assessment of model fit, which I think is valuable in terms of these large data sets with high variation in the different gene topologies that you're seeing. And then I also am really excited to actually get results back, hopefully soon, for at least the molecular data, looking at the model fit across genes, and also thinking about doing the same for the morphological component. And I went through that quite quickly, but I'd like to thank specifically my fellow Rev-based users and developers. Sebastian's been amazingly helpful, as well as all the other additional feedback and support from the wonderful people at LSU. I'm glad I finished very quickly, but I'll take any questions.
So your input's a multiple sequence alignment, and that you're treating that as what you observe, but it's also estimated.
Meaning in terms of alignment?
Yeah.
Yes.
So have you considered starting from the actual sequences and going through a longer process?
Yeah, so the question was about looking at, because multiple sequence alignment has already used a model basically to get there. And no, I think that would be a really interesting thing to do. So basically doing the model check also on how to align. No, but I think that'd be really valuable to set up.